At lunchtime on January 15, 1919, people in Boston's North End heard a metallic roar. A steel tank split apart and released about 2.3 million gallons of molasses. Witnesses described a dark wave roughly 15 feet high, moving at an estimated 35 miles per hour. Buildings broke, elevated rail supports bent, and people were swept into debris. 21 people died and around 150 were injured. The Great Molasses Flood sounds like an invented headline. Its real story is an engineering warning about leaks, ignored tests, weak steel, and the legal battle that changed who had to prove a structure was safe. This is Pip's Fact Orbit. One familiar fact, and a much stranger story. The tank stood beside Boston Harbor on Commercial Street, surrounded by homes, workshops, a firehouse, freight yards, and an elevated railway. It belonged to the Purity Distilling Company, later controlled by United States Industrial Alcohol. Molasses arriving by ship was stored there before being moved to a plant in Cambridge, where it could be turned into industrial alcohol. That industrial purpose matters. During the First World War, alcohol was valuable for munitions and other manufacturing, and the company wanted large, fast storage close to the waterfront and rail network. The tank was not a novelty built for food. It was part of a busy supply chain, and every delay cost money. Commercial urgency explains why the schedule was tight. It does not excuse skipping proof that the finished structure could safely hold its load. This was a huge industrial container placed inside a crowded neighborhood. The cylinder was about 50 feet high and 90 feet across, large enough to hold roughly 2.5 million gallons. When nearly full, the liquid inside weighed thousands of tons. Even a slow liquid creates enormous pressure at the bottom of a tank that tall. The warning signs began before the disaster. The tank was built quickly in 1915 because a shipment of molasses was already on its way. According to later testimony, it was not filled with water for a complete leak test before entering service. Almost immediately, molasses seeped from its seams. Residents collected the drips in containers, and workers tried to manage recurring leaks rather than treating them as evidence of a dangerous structural problem. People also heard the tank groan and rumble as it was filled and emptied. Metal tanks do make sounds as loads change, but repeated leakage and distress should have triggered an engineering investigation. Instead, the tank remained in service through years of filling cycles. Each cycle raised and lowered the stress in its plates and riveted seams. January 1919 added another complication. Boston had experienced bitter cold, then the air temperature rose rapidly to around 40 degrees Fahrenheit. A fresh delivery of warmer molasses had recently entered the tank. Temperature affects viscosity, the resistance of a fluid to flowing, and it can also influence fermentation and pressure. But modern engineering analysis does not need a mysterious internal explosion to explain the failure. The container itself was dangerously weak. At about 12:40 in the afternoon, the tank tore open. Steel plates peeled away and rivets reportedly flew like projectiles. The collapsing wall released a liquid mass with the weight and gravitational energy of a small reservoir. The phrase slow as molasses became completely misleading. Viscosity resists motion, but it cannot gently restrain millions of gallons dropping from a 50-foot tank all at once. The often repeated 35-mile-per-hour speed and 15-foot height come from contemporary reports and later summaries, so they should be treated as estimates, not measurements from modern instruments. The physical conclusion is not in doubt. The first surge moved fast enough to smash wooden buildings, shove a firehouse from its foundations, damage freight cars, and bend parts of the elevated rail structure. The scene became deadlier as the molasses spread and cooled. Harvard researchers later studied how temperature changes the flow. Molasses is denser than water and can be thousands of times more viscous. The leading edge could initially move rapidly under gravity, then thicken dramatically as it cooled in the winter air. Victims who had been knocked down faced a dense, sticky fluid that resisted every movement. Rescuers struggled to walk, lift debris, and keep their footing. This two-stage behavior resolves the apparent contradiction at the heart of the story. A large column of liquid can convert height into speed at the moment of release, even when that liquid is syrupy. Once it becomes a shallow layer, gravity provides less force to keep it moving. Cooling then raises the viscosity, so the same material that hit like a fast surge can become an exhausting trap. The flood was both quicker and slower than everyday intuition expects. At different moments, firefighters, police officers, sailors, medical workers, and residents entered the wreckage. They used ladders as makeshift walkways and worked through a mixture of molasses, broken timber, twisted steel, and shattered vehicles. The disaster killed people ranging from children to older adults. It also killed horses trapped in the flood. Treating the event as a quirky joke erases what the North End experienced: a preventable industrial collapse in a working-class and heavily immigrant neighborhood. Cleanup was another engineering problem. Ordinary cold water was slow against the syrup, Crews used salt water pumped from the harbor, hoses, sand, shovels, and scrapers. Boots and wheels carried sticky residue onto streets, trains, telephones, and buildings far beyond the impact zone. The Boston Public Library's archive estimates more than 87,000 labor hours went into removing molasses from the neighborhood. Almost immediately, the company suggested sabotage. The United States had seen anarchist bombings, and the company argued an explosive device had destroyed the tank. That claim shifted attention away from construction and toward an invisible attacker. Families and property owners filed claims, which were combined into a major civil proceeding. The hearings became one of the longest and most technical legal investigations of their time. Engineers, metallurgists, witnesses, and company officials argued over explosions, fermentation, rivets, plate thickness, and design calculations. Court-appointed auditor Hugh Ogden ultimately rejected the sabotage theory and concluded that structural failure caused the disaster. United States Industrial Alcohol was held responsible and paid hundreds of thousands of dollars in damages and settlements. Ogden's finding also mattered because the failure could not be dismissed as an act of nature. The danger came from decisions that could be examined: who designed the tank, which calculations were performed, what testing was skipped, and how the owner responded to visible leaks. Turning those questions into evidence gave the victims a path to accountability instead of leaving the collapse as an unexplained tragedy. Later engineers have revisited the evidence with tools unavailable in 1919. Structural and metallurgical engineer Ronald Mayville found several weaknesses working together. The tank walls were too thin for the load. Stress concentrated around rivet holes and a large manhole near the base. The steel's chemistry made it more likely to fracture brittly in cold conditions. Repeated filling may also have allowed cracks to grow over time. This matters because disasters rarely have one cinematic cause. A temperature swing did not make a sound tank explode. Fermentation alone did not excuse weak construction. The catastrophe emerged from rushed work, inadequate testing, insufficient safety margin, vulnerable material, high local stresses, and years of warning signs that were normalized. The legal outcome helped strengthen the idea that large structures needed qualified engineering, documented calculations, official review, and accountability after failure. Building regulation was already evolving, so the Molasses case did not single-handedly create modern codes, but it became a powerful example. A company could not simply erect an enormous industrial structure beside homes and then blame an unknowable accident when it failed. Today, the tank is gone. A small plaque near Langon Park marks the location, and the waterfront has been rebuilt. The claim that people can still smell molasses on hot days belongs more to local folklore than measurable evidence. The photographs, however, are unmistakable: twisted track, crushed buildings, and curved sheets of steel lying across the street. So how could molasses move fast enough to destroy a neighborhood? Gale. Millions of gallons held high above the ground stored enormous potential energy. When a structurally inadequate tank opened, gravity accelerated the first surge before winter cooling made the fluid thicker and rescue harder. The strangest part was never the substance. It was that a leaking, growing tank full of warning signs was allowed to stand until the neighborhood paid the price.